Hey there. Do you mind if I ask you something? What do you eat for breakfast every day? Oh. Yeah? Wow, that sounds yummy. Send me that recipe if you don't mind. You see, I'm asking because I've been in a really big rut lately. Every morning, I toss in a little bit of oil into a frying pan and use that to scramble up one egg. It's getting a little old. But out of the repetition, I've noticed something. The oil that I use always remains as a thin layer on the bottom of the frying pan. Take a look real quick, because I removed part of the frying pan so you could see a cross section. I put a little thin layer of coconut oil, because coconut oil is normally what I use whenever I'm cooking my eggs. I can be quite lazy. There's a million things to do every morning, am I right? So it would be nice if I could clean this frying pan with as few steps as possible, namely without bothering to add any soap. But try as hard as I might, no matter how high the water pressure is, no matter how hot the water is, that coconut oil is impervious. The water just deflects right off of it. And even if I kept at it until the room flooded, look at that. There's still that thin layer of coconut oil. The oil is unfazed. So would you say it was stubborn? I actually wouldn't. Oil and water simply don't mix together. They don't mix so much that if I had filled this frying pan with water, the oil would have floated on top. And I love seeing this. There are some laboratory experiments that require you to fill a test tube with both water and oil. The water layer always ends up on the bottom, and the oil's on top. And I never once got tired of seeing it. This line right here of division is so trippy to look at. It's like magic in real life to see two liquids, one floating on top of the other. But let's go ahead and move on to the phrase we're all waiting to hear: like dissolves like. And much like Hakuna Matata, this is a wonderful phrase. It means no worries. Anyone can quickly find out if something will dissolve in something else. The phrase like dissolves like is functioning as expected in this example because water and oil are too different to interact with each other. I'd love to show you just how dissimilar they are. So please, allow me to show you what water molecules and oil molecules look like up close and personal. Now, a microscope is just not going to cut it. I mean, this is for looking at cells, not atoms or molecules, which are many more times smaller. We need something stronger. Much stronger. Okay, if you know me from before, I've been out of the YouTube game for about 5.5 years, but I haven't been sitting around doing nothing. Allow me to introduce a powerful new tool. Not a microscope, but a picoscope. Yes, this is my wild and crazy invention, and I can't wait to show it to the world. With this bad boy, we're going to be able to look right at that molecular structure. So let me grab it here and... Whoa! It's so dark down here without any photons. A little spooky. Well, alright, cool. We already found the water molecules. The bigger circles are oxygen atoms, while the smaller are hydrogen. Oh yeah, that makes sense. Wow, we're really finding them, aren't we? And not one oil molecule in sight. You see, water is extremely polar because of the electronegativity of the oxygen and the overall shape of the molecule. So it's for these reasons that water has a permanent dipole moment. Okay, let's head on up to the oil layer. It should be up here somewhere. I guess we're heading through the no man's zone right now, that very clear division that I showed before with the line. But the oil's here somewhere, and here we go. We found some. Now, I had to zoom out because oil is so much bigger of a molecule. All of those green carbon atoms amount to no polarity. And note the size, but let's go back up to the whiteboard and discuss this a little bit more. So, like dissolves like. We've already seen it with the frying pan example. And for us, we are talking about a polar molecule, which is water, and a nonpolar molecule, which is and oil. Now, this is a little bit deceiving. Let's shrink this water molecule down so that it is comparatively having the same atomic size as our oil, and you can see the stark difference. The water molecule is small, which gives the oxygen atom total dominance, and it creates a permanent dipole moment. Whereas with the oil, there are a couple of oxygens, you can see those white circles there. However, they just don't have the power. Instead, the power is with the carbon atoms. And there's so many of them that they generate a massive electron cloud. And they will dissolve with other oils because of London dispersion forces. I know it's a lot to take in. Even whenever I was first starting with chemistry, I was really hung up on the fact that the oil molecule does have oxygens, which is electronegative, but it helps to think about the real world. So don't forget that oil and water don't mix. Water will dissolve with another polar thing, like think about acetone. The very common example people like to give is about fingernail polish remover, where it's actually the acetone that's the major product with the water dissolved into it to dilute it a little bit. Likewise, the oil here will dissolve in other oils, and to be completely honest with you, the oils that we use for cooking are never purely one molecule. They're a mixture of different things like oleic acid, palmitic acid, stearic acid, a few others even. They all have the same characteristic, very long body. A chain made out of carbons, as I'm showing here with this zigzag haphazard line. But I know why all of you clicked on this video. You're wondering, what if you forced water and oil to dissolve each other? You're starting to talk a little bit like a mad scientist. In other words, we're not talking about like dissolves like. No. We're talking about dislike dissolves. Dislike. Okay, enough of that. No more goofing off. We need to come up with a plan right now in order to break one of chemistry's biggest rules. So, I got my little grocery list here. Obviously, we want to make water and an oil dissolve together, so they're the first two items we need on our list. And I have a secret ingredient. Don't go sharing it with anybody. The other thing we need is an emulsifier. The emulsifier I'm going to choose is called emulsifying wax. Yeah, I know. Not much of a secretive name, is it? This item that anyone can buy right off the shelf is a mixture of two separate things. One is cetosterol alcohol, and the other one is sodium lauryl sulfate. Neither of these molecules seem like they would be soluble in water. However, the sodium and sodium lauryl sulfate does fully dissociate away, just like a salt, sodium chloride, leaving behind a negative charge on that giant molecule. And both of them have a long carbon tail, which makes them also soluble in oil. Together, they're soluble in warm water. So, let's make sure this actually works. We're going to pull out a formula, some of our favorite things, right? We have the water plus the oil plus our emulsifier, which we just went over. With all of these things combined, we are going to make our product. What kind of horrifying abomination of nature do you think you're about to see? I bet you weren't expecting lotion. It's pretty wild, isn't it? That breaking the law of like dissolves like leads to one of the most common things in the world. I mean, we could all walk into any convenience store and pick up a bottle of lotion. The lotion has a really cool thing about it because it is water and it is oil, so you can put vitamins that are only soluble in one or the other into one product. The water-soluble stuff could be like vitamin B and vitamin C, whereas your oil-soluble stuff could be like vitamin A and vitamin E. So I encourage you to look at the lotion that you use constantly, look at the list of ingredients, and be amazed. Thanks for watching, and until next time.